Hello, this is S. Roy again. We are in lecture 1 of Haskell module, and this is just to remind you that at PGSU we are using this textbook 7 Languages in 7 Weeks by Bruce Tate. We have been using for this semester 2020 spring, and same book we have used in for the Scala module, and also we are using for the Haskell module. Maybe I forgot to mention this textbook in my Scala module lecture videos, but that was implicitly assumed. Okay, so many of the examples shown in these videos of these Scala modules and Haskell modules use material from this textbook as you expect, and this is just to avoid confusion. I am announcing this explicitly. Okay, so now let's move to our part 2 of lecture 1. And there we start recursion in Haskell, and this is one example. We are writing this recursive function fact, which takes one parameter x. So we are trying to compute the factorial of x, and the body of this function is this remaining part on the right hand side of this equals symbol. And let me read it. If x equals 0, then we return 1, else we return a recursive part. There we are calling this same function fact with x minus 1 as the argument, and multiplied with x. That is as expected. And now it's ready to use. So to compute the factorial of 3, we just write fact 3 get 6. Now if we want to write this function in a file, and maybe this time we can use another style of writing the same function, and that is called pattern matching. So here we can see there are two patterns of the input. If the input is 0, then this function is returning 1. Otherwise, which is the second line, we are going to return this one where the recursion is happening. Correct? So this style, which have two cases, called pattern matching. We also saw similar pattern matching in Scala. Another thing we are explicitly mentioning here in this line, we say the type of this function factorial is as follows, and this part is talking about the input type. So the input is an integer, and then arrow means we are going to talk about the output type, and that is also integer. And what is integer? Integer is an arbitrary length integer which is available in Scala. That means never overflow happens in this integer. If your value is bigger, Haskell automatically gives you more space to store that value, and never overflow happens. That's a cool feature, right? And if you need that feature, you are going to use this big integer. Haskell also has small int, just int, and that has a fixed size. This arbitrary space is not available there, and that is the difference between this big integer and just int. Okay, now we can move to the next style of writing the same function, and here we are using guard concept. Basically that means using if condition. So when the parameter x is greater than 1, then it will come here. This vertical symbol is called guard. So that means we are guarding that condition, and if that condition is true, then this will be the return. Otherwise, another guard symbol, we are going to return 1. And here also the type information is available. Now we can also try to implement Fibonacci implementation in Haskell, and there we are using pattern matching. So fib 0 is 1, fib 1 is 1, and otherwise we have fib n minus 1 plus fib n minus 2. And now this looks okay, but a problem is there are too many function calls in this implementation. So what I mean is just to compute fib 6, this sort of calls will happen, right? We'll call fib 5 and then fib 4, then fib 5 will in turn call fib 4, fib 3, fib 4 will call fib 3, fib 2, and so on. And you can see that number of calls are increasing exponentially, kind of, correct? So you can imagine if we want to calculate fib 100, there will be too many calls, and one regular laptop will not be able to handle that. So this implementation of Fibonacci has severe limitation, space problem, and I should say the number of function calls are too many. Okay, now how to make the fib implementation better? We can do many alternatives. So here is one. We are defining a function fib tuple. The input is a tuple, and that has 3 components. Each component is an integer. Output is also a tuple, and each component is an integer. There are 2 cases. If input is x, y, 1, then that will be the output. Otherwise, that means this last part is not 1. Last part is index. If index is not 1, then there will be recursion. And you can see what is happening in this recursion. We are going to reduce index by 1. More importantly, these first 2 are getting replaced by the next pair of Fibonacci number. You can see that, right? Y comma x plus y. So at the place of x, we are writing y, the next one, and at the place of y, we are writing x plus y, the next one, right? And just to remind, I am assuming the Fibonacci series starts from 1. Second item is also 1. And third item is 1 plus 1, 2. Fourth item is 1 plus 2, 3. Fifth item is 2 plus 3, 5, and so on, right? Okay, now let's see what happens when we call fib tuple with 1, 1, and index 4. Then which case this call matches to? This does not matches with 1, case number 1, right? It will match with case number 2. So we are here. So that means this will happen. And that means we are going to call 1 because y was 1, and x plus y, which is 2, and index got reduced to 3. So now this call will happen, correct? Now again, we have to see which case of fib tuple matches with this, and still case 2 matches with this, right? And now mind that x value is 1 and y value is 2. So then that means the next call will be 2 comma 1 plus 2, 3, right? So 2 comma 3 and index will be 2, which is written here. 2 comma 3 and index will be 2, right? And similarly, that will again call 3 comma 5 and index will be 1. So you can see that the first 2 components of these calls are having the next and next Fibonacci pairs, correct? Where the third parameter is the index, and that is getting reduced by 1 in each step, correct? Now this last one will match with case number 1, and then that means that should return 351. So we started with index 4, that means we wanted to calculate the fourth Fibonacci number, correct? And we are getting that as the first component of this return, correct? So now what job is left? After getting this output, we have to just extract the first component, which is easy. We can just write another helper function, say fib result, given 3 things as a tuple, it will just return the first thing. Now if we combine these two functions together, so we had fifth tuple in the previous slide, which we call with 1 comma 1 comma n when we want to compute nth Fibonacci number, and we know what it returns. We saw that in previous slide. And then in this helper function fib result, we are going to extract that first part, the first component, which is the answer, which is the nth Fibonacci number, right? So that gives us this final implementation of this function fib, correct? Maybe it's a good idea to test what we discussed. So let me copy quickly this one, and let me go to my Haskell module. Let's get it clear, and let me go to this function, and let me copy and paste the code. So we pasted fifth tuple. Now it's a good idea to get this other helper function fib result, and then the final implementation, this fib, right? And then maybe it's a good idea to have a main where we are going to print whatever fib number we want. Say we want the fourth Fibonacci number, so that's why I'm writing, I'm calling fib4. Makes sense, right? Okay, so let me save it, and now we can load it and compile it this way, and then I can call main, and that gives me the answer. So this works, right? Okay, let's move forward. And next discussion topic is how to compose two functions. Here head is one function, and given a list it returns the head of the list, where tail is another function. Given a list it returns the remaining part of the list except head. Now if we compose these two functions with a dot in between, that gives us the composition. These two functions together, the effect will be there. Now let's call that composition function as second. Okay, and now if we apply second on a list, then that will give you 2. If you apply that on another list, here also it will give you the second element of the list. And why that is happening? Because this second is nothing but this two functions composition, which is equivalent to, given a list, first apply tail. That means given a list, first apply tail, that is 2 as a list, and then apply head, which is head of 2 is 2, right? And for this case, the tail of this list is 4 and 5 as a list, and head of that is 4, and that's why we are getting 4. Make sense? Okay. Now let's get another Fibonacci implementation, and maybe we'll also run that implementation to calculate a bigger Fibonacci number. Here we have one function called fibNextPair. Given two Fibonacci number x and y, it gives us the next pair of Fibonacci number, which is y comma x plus y. And we have another helper function fibnth pair, and base case is 1 comma 1, and for n as the parameter, fibnth pair calls fibNextPair, and inside there is fibnth pair in minus 1. So I think we need an example to explain this, right? Say this is an example. We are calling fibnth pair with parameter 8. Then what will happen? Let's discuss that. Maybe 8 is too big. Let's make it 4, and let me discuss what will happen when we have the call fibnth pair with parameter 4. So that means the right hand side of the function tells us this will happen. So if I just write that down, that means this is going to happen, right? Fibnth pair with 4 minus 1, right? That was the direct copy of the right hand side, correct? And that means the call is to fibnth pair 3, and whatever is the result, then fibNextPair will run on that, right? Now again, more recursion to resolve, right? So fibnth pair 3 is what we have now, and we have to evaluate that. That means again we have to apply this formula, right? So let's do it again. So I'm going to replace this with again the body of that recursion call, and where n is 3, right? So after simplifying that, we have this. So now I think you are seeing the pattern, and after doing the same thing with fibnth pair 2, so again we can copy that, and let's put it in here with 2, replacing that with 1, we have this, correct? Then fibnth pair 1 is matching with this case, so instead of that we can replace that with 1 comma 1. Now we are done with this helper functions, and now we have fibNextPair 1 comma 1, which is matching with which means we are going to apply this rule, right? So fibNextPair 1 comma 1 basically means whatever is written here, and that means if you just replace the values, then that means 1 comma 2, correct? And again fibNextPair of 1 comma 2, where x is 1 and y is 2. So if you do the replacement, then you see that it will be 2 comma 3, correct? And then doing the same thing again, so x is 2 now, y is 3, and that means after this is done, we will have 3 comma 5, correct, as the final output. So see how things are happening. And now that our answer is just 3, the fourth value of the Fibonacci series. So we have to extract that part. Similar situation as we have seen before, right? So we can have a helper function which takes these two parts as a tuple and returns only the first part, correct? And then this is the final implementation, which composes this helper function take first with dot and the previous function what we discussed, the fifth nth pair. Correct. So this implementation of Fibonacci implementation is using this composition feature. And now to run it, we can run it with parameter 4. So fib4 in print, we can call it main, and now we should be ready to apply. So let me copy this. I think everything is here. So let me copy that and go to my file, and there I can replace this, and to reduce clutter I can take out those comments, and here you go. Right, so this was the fib next pair implementation. Then we have fib nth pair, which is a recursive function, right? And then we have this helper function take first, and then we have this composition here, and that gives us the final implementation, and we are calling that with parameter 4. So we are expecting the fourth Fibonacci number as the output. So now let me run it, and we can call main, and we are getting that output. Now we can also call that fib function from here, right? And say we want to compute the 100 Fibonacci number, which is a huge number. Maybe before going to 100, let's take 20, which is this much. Then let's take 50, which is this much. Now fib 100 will be a huge number, correct? And let's see whether my laptop is able to handle it, and it is able to handle, and we get it very quickly. Even maybe 5,000 it will be able to handle, and we get this big number, and this is accurate result, and no overflow has happened in our integer data structure. That integer type, remember, we have used, maybe I go to the file again, I'm talking about this type, and as I said, that is with arbitrary length, and no overflow has happened. So the result which we have got for Fibonacci 1000, that is an accurate result, and if you remember, it just took maybe 1 second to compute. So it's a huge plus compared to the rudimentary implementation which we have seen before. By before, to be clear, I mean, let me go back. Compared to this one is problematic, right? As there are too many calls. Okay, so I guess we got the idea, and let's move to the next topic, which is an easier one, how to work with list. We already worked with list in Prolog in Scala. Let's see how Haskell handles it. Given a list, you can deconstruct the list with this head tail construct, and this means head h is 1 and tail t is the rest of the list as a sublist, right? And mind that head is not a list, but tail is a sublist. Okay, now let's write some simple recursion on how to process a list. Say we want to know the size of a list. This can be the implementation of the size function. There are two cases. If the list is empty, then size is 0. Otherwise means if the list is not empty, that means we'll be able to deconstruct it in head and tail. And in that case, the size of the list will be 1 plus the size of the tail, right? Because head has just one element, so whatever is the size of the tail, if somehow magically by recursion we can get it, then just adding 1 with that will give us the ultimate result, correct? We have seen it in many other languages before. And how to compute the product of a list of, say, integers. So we can first make product of an empty list as 1, and this is just to define the base case, and then product of a non-empty list is head multiplied with product of the tail. So whatever is the product of the tail part, if we just multiply that with head, that is going to give us the product of the full list, correct? Easy. Now if you call this function size on a string, fascinating, then it works. Why it works? Because remember, a string is nothing but a list of characters, and if you count, there are 12 characters, and that's why size is returning 12, because this function says whatever is the size of the list, that should be the return. Okay, now let's talk about a couple of ways how we can generate a list. With some examples, we'll run this discussion. Say we want to write a function, name is all even, and what does this function do given a list of integers? Given a list of integers, this function all even gives us the sublist of even integers which were present in the input list. Make sense? So that means if an input list has 5 even integers and 3 odd integers, this function all even will extract only those even integers as a list and will leave out the odd integers. What will be the recursive implementation of this function? If the list is empty, then that can be the return, right? Makes sense. And if the list is non-empty, then let's deconstruct that in head and tail. So in that case, we have to check if head is even. If head is even, then the result should be, the output should be head concatenated with whatever even numbers we have inside tail, right? So that means this should be the output, head, which is even, we already checked, concatenated with this colon is the concatenation symbol for concatenating head with a list, and then this part means the same function applied on the tail, so that should magically give us, by the virtue of recursion, that should magically give us what are the integers present in tail which are even, right? So then we should just concatenate these two parts, and that should give us the final answer, right? Else, that means head is not even, so we should forget head. We should only call this all even function on the tail part, and whatever is the result, that should be our final result, right? Okay, so I think we got the idea, and this also shows, not only we understand this interesting implementation of a example function all even, we also understand this syntax, how to create a list, how to generate a list. We understand this colon construct, right? Okay. There are ranges available in Haskell. It was also available in Scala, right? And here is an example. This is a list where which starts with 10, next element is 8, then dot dot, means it can go on, and the last element is 4. Then Haskell can figure out that the list is 10, 8, because it decrementing by 2, so the next element should be 6 and the last element is 4, so this has to be the list. And this construct, the dot dot, we call it range, right? Now, not only with integers, with fractional number also this can work, and Haskell will figure out the interval like this, right? And you can also talk about an infinite list. So this part means a list which starts with 1, and dot dot means the default increment value is also 1. That is always the default increment value. So that means in this part, the next item in the list is 2, next is 3, next is 4, and so on. This is an infinite list. And here we are saying we want to take only the first 5 values in that infinite list, and that's why this is the answer, right? So this has basically 2 parts. Similarly, here this is an infinite list starting with 0, next element 2, so next will be 4, next will be 6, and so on, and we want to get only the first 5, and that's why this is the result. Okay, so you can see that using range also we are able to get a list, we are able to compose a list, right? That was the topic here. Another way to compose a list is called list comprehension, and here is an example. So the right hand side is called generator. So X is getting generated from this list 1, 2, 3. So X can take value of the first item, then the second item, then the third item in sequence. Okay, and then the left hand side is an expression, and whatever is the evaluation of that expression with those different values of X, that will be returned as a list. So first value of X is 1, so here this expression evaluates to 2. Next value of X is 2, so here it evaluates to 4. Next value is X is 3, here it evaluates to 6. So this will be the final list, and this style is called list comprehension. Here it can be more complicated. So XY is a tuple, and that is getting generated by these elements in this list. And mind that here one element in the list is a tuple. So the first value of XY is 1, 2. Next value of XY is 2, 3. And those are getting generated. And then in the expression we have reverse tuple y comma x, and that's why when xy is 1, 2, we generate 2, 1 here, and so on, right? Okay, we can also have a more complicated expression here, right? I think it's self-intuitive. After getting x and y, you can have 4 minus x, right? And y can remain same. And here crew is a list of words, and then A is getting generated from crew, B is also getting generated from crew, and you can also have a condition in this right hand side. So A is less than B, that means A, this word should appear before the word B in the dictionary, right? In alphabetical order, and the expression is A comma B. So if you do the calculation, you see that one possibility is A is Kark, and one possibility is B is spoke, and that satisfies A less than B because Kark starts with K, spoke starts with A, so Kark is less than spoke, right? And that's why that is one possibility, one value which is getting generated, right? And another value of B can be McCoy, and that will give us this. Also another value of A can be McCoy, and B can be spoke, and still A less than B, and that will give us the third generated element, right? And these three elements together will be the final list. Okay. Now to run Haskell, of course, first you need to install this Haskell compiler, a Haskell interpreter. Different operating system have different ways of that installation, and here it is discussed. Should be simple. And after you install the Haskell interpreter, you can just run GACI command, and that will start the interpreter. We can also call it Haskell console. And there on the Haskell console, typically which comes with this symbol prelude, and there you can type an expression. So we can type this if full clause, and that will, as this is the true statement, right? So this should return true. And then you can also define a function right there. So double is a function, and then you can call double, and that should give you the result 4, right? So on console you can do your work. And of course, when your code is bigger, or if you want to work only in the file, of course, then start your file, say double.hs, and there write the code, and then you can load that code from your console. Okay, like that. And say not only you want to work with the interpreter, you also want to compile your code to generate an executable, and then this is the way to go. So write your code in a file. Say this one is factorial implementation, write it in a file called factorial.hs, and then in main you can have a do block, and there you can call this factorial with parameter with argument 10, and that result will be in x, and then you can print x. So this code has a main method, and when the code has main method, then you can compile it using this GHC command, and then the executable name, you can give a name. Say here I am giving the executable name myFAQ, and you have to use O flag for that executable name, and this is the input text file which has this Haskell code, right? So this is the command to compile the Haskell code, and after that is done, that means it will generate your executable, and you can run your executable, and that should give you this factorial of 10, right? So this is how we can get an executable, and you can directly run without using the interpreter. And that's it for now.